Okay, so let's dive into this. Climate change is right there, the defining challenge of our time, and the global goal set by the Paris Agreement is pretty crystal clear. Keep global warming well below 2 degrees Celsius, really pushing hard for 1.5 degrees compared to pre-industrial levels.
And the hard reality, as this source material we're looking at today lays out, is that current emission rates, like in that high RCP 8.5 scenario, they put us on a path for 4 degrees C warming or maybe even more.
Wow.
Yeah. And even if you just look at the current national commitments, we're still projected for around a 3 degrees C rise.
Right.
That's a huge gap for those targets we need to hit.
Right, a really big gap. So the IPCC reports, which the source references, they really don't pull any punches, do they? Massive emission reductions are, well, absolutely non-negotiable.
Totally non-negotiable.
But they also say that carbon dioxide removal, or CDR, is also going to be essential. We're talking about potentially needing to pull somewhere between 100 and 1,000 billion tons of CO2 out of the atmosphere by 2100. That scale is just immense.
It really is. Yeah. And it's important we get precise on what CDR means. You know, using the IPCC definition the source relies on here, it's specifically about human activities. Activities designed to extract CO2 that's already in the atmosphere and then store it durably.
Right. So it's different from carbon capture and storage, CCS.
Exactly. CCS captures emissions at the source, like, say, a factory smokestack, before they even get into the atmosphere. CDR is about cleaning up what's already there, decreasing the total amount that's accumulated over time.
Got it. Okay. So our source material for this deep dive is actually a master's thesis, and it really zeroes in on selected CDR technologies and applies a very specific analytical tool to them, a SWOT analysis.
Yeah. Strengths, weaknesses, opportunities, threats. And our mission today is basically to walk you through that analysis. We're going to explore the SWOT findings for several key CDR technologies, all seen through the lens of this thesis.
So what does this particular analysis suggest are the most promising paths forward right now for removing CO2, to help hit those Paris Agreement goals? What insights jump out, and where does it get really interesting based on the data they pulled together?
Well, the thesis took several specific CDR technologies and put them through this SWOT framework. It's a pretty standard way to break things down, right?
Yeah, very common.
And the author compared them across a whole suite of factors. Then they assign these qualitative scores. You can think of it like a traffic light system, green, orange, or red, just to summarize how each technology stacked up on each factor based on the data available.
Okay, and what kind of factors are we talking about?
Oh, a whole range of crucial stuff, like durable storage, basically. How long does that captured CO2 actually stay locked away? Is it decades, centuries, or even millennia?
Okay, durability. What else?
Technology readiness level, TRL.
Yeah.
And that's a scale, from 1, which is just basic research ideas, all the way up to TRL 9, which means the tech is proven, it's out there, it's deployed.
Right. How mature is it? Makes sense.
Then there's cost at scale, a big one. The estimated price per ton of CO2 removed. Mitigation percentage. So what's the potential annual capacity in gigatons of CO2? How much could it actually do?
And MRV. I saw that abbreviation.
Oh, yeah. MRV monitoring, reporting, and verification. Basically, how easy and accurate is it to actually measure that the carbon has been removed and, importantly, that it's staying removed?
Gotcha. That sounds critical for trusting these methods.
Definitely. Plus, they look at associated risks, obviously.
Yeah.
Energy requirements, how much power does it need, the level of R&D activity, looking at things like publications and patents.
And social acceptance. How did they measure that?
That was interesting. It was based on analyzing Twitter data in this thesis.
Yeah.
And finally, the broader context, the landscape of policymaking and investor incentives. So, yeah, a pretty robust set of criteria.
It really is. That gives a good framework for comparing what seem like very different approaches.
It does. And right out of the gate, the thesis conclusion points to 2 technologies that, based on its analysis, seem to have more potential than the others in this detailed comparison. That's direct air capture with carbon storage, DACCS, and Afforestation, Reforestation, ANR.
Okay, let's start with DACCS then. Direct air capture with carbon storage. So this is the chemical engineering approach, right? Building machines that literally suck CO2 out of the regular air around us.
That's the one. And then the captured CO2 needs to be stored somewhere permanently. A key point the source makes is that, unlike capturing from a power plant stack, DACCS isn't tied to an emission source. You could potentially put these plants anywhere you have access to energy and suitable storage.
Oh, okay. So location flexibility. What did the analysis say were its strengths?
Well, looking at the strengths from the analysis, there are quite a few positives. It scores highly for technology readiness, marked green in the thesis tables. Some systems are apparently already at TRL9.
Wow, so ready to go, technically.
Pretty much. It also gets a green for durable storage potential. The analysis says geological or mineral storage offers the longest possible duration we know of, maybe 10,000 to 100,000 years.
Okay, that's incredibly long-term storage.
Yeah. And the measurability, the MRV we talked about, also rated green. The source finds it's precise and relatively easy to do for DACCS.
Good.
Its scalability potential is estimated to be high, potentially 40 GDCO2 per year or even more, another green mark. And therefore, a high potential contribution to hitting that below 2 degrees C target, also green.
And risks.
Risks, specifically the likelihood of CO2 leaking back out from that geological storage, are considered low and marked green. So yeah, that's a lot of green lights.
It really is. High TRL, super long storage, massive potential scale, measurable, low risk. Sounds almost perfect. But I'm guessing there's a but.
There's definitely a but. The analysis also points to some pretty significant weaknesses. Number one, high energy requirements marked red. Pulling CO2 out of the air where it's very dilute, that just takes a lot of energy, heat, and power. Now, the source does mention this risk is maybe reduced if you're using renewable energy sources, but the sheer amount of energy is still a major factor.
Okay, high energy needs. What else?
And critically, the cost is high, marked red. The source mentions current costs below $600 per ton, and while those are projected to come down, even the future projections are still high compared to many other potential methods.
Right. That really puts the brakes on, doesn't it? High energy needs and high cost. So why are those such persistent hurdles right now? I mean, if the tech is ready and the scale potential is huge.
Yeah, that's exactly where the sort of economic and energy infrastructure realities really kick in. While the chemistry works, getting the huge amount of energy needed cleanly and getting it at a low enough cost to process these vast amounts of air economically all over the world.
Yeah.
That's the major challenge.
So it's less about can we physically do it and more about can we actually afford to do it everywhere and without just causing emissions somewhere else from the energy source.
You've got it. That's what those red scores for energy and cost really highlight in the analysis. It's a big economic and logistical puzzle.
Okay, interesting. What about the opportunities and threats side of the SWOT?
Well, R&D activity is kind of mixed, rated orange. There seems to be high patent activity, which suggests commercial interest is picking up, but maybe a lower share of academic publications compared to some other methods. Perhaps less fundamental research is needed now, more engineering.
Maybe. And social acceptance.
Also orange. The Twitter data analysis showed relatively low general public awareness of DCCS, but among those who were tweeting about it, the sentiment seemed generally positive.
Okay. And the big structural issues.
Yeah, a big weakness identified as policymaking, marked red globally. And related to that, a lack of investors, marked orange. The source does mention some positive steps like U.S. tax credits and some EU and UK innovation funds, but dedicated global policy support is still really just starting.
That makes sense. Even if the tech is ready, you absolutely need the policy push and the investment to actually deploy it at the kind of scale we're talking about.
Exactly.
So for you, the listener, thinking about DACCS based on the source, it offers this incredible potential, right?
Yeah.
High-tech readiness, truly permanent storage, huge scale. Those are its big wins, according to this analysis.
Right.
But the analysis really emphasizes that the high energy requirement and the high cost are the fundamental barriers right now. They're standing in the way of immediate, widespread deployment. It highlights those economic challenges just as much as the technical ones.
Well put. Okay, now let's shift gears to the other one highlighted, Afforestation and Reforestation, A&R. This is, planting trees. Either planting them where forests haven't been recently, that's afforestation, or replanting where they've been removed, reforestation.
Trees. This feels like the most familiar, maybe the most intuitive approach to carbon removal for a lot of people. How did the analysis rate its strengths?
A&R also scores highly on several factors in this analysis. It's rated high TRL, with some applications definitely a TRL 9. We know how to plant trees.
Sure do.
Energy requirements are low, marked green. Trees mostly do their own thing using sunlight, right? Measurability, the MRV, can be precise and easy, also rated green.
Okay.
Scalability potential is high, estimated up to maybe 18 GTCO2 per year or more, marked green. And consequently, a high potential contribution to the below 2 degrees C target, another green.
And social acceptance, I bet that's high.
You bet right. Rated high, marked green. The source's Twitter analysis showed medium to high awareness compared to others and very positive sentiment, People generally like trees.
Can't argue with that. So high social acceptance, low energy needs, high potential scale. That sounds incredibly promising on the surface.
Right.
What are the weaknesses or challenges the analysis brought up?
Yeah, here's where the big questions come in, particularly around durability. Durable storage is rated lower for ANR, marked orange. Carbon stored in trees and soil typically lasts maybe from 10 up to 1,000 years, which is significant, but not geological timescales.
Okay, so less permanent than DACCS storage.
Definitely.
Yeah.
And crucially, this storage is vulnerable to reversal. The analysis flags risks like wildfires, disease, pests, things that can release that stored carbon right back into the atmosphere, sometimes very quickly. This reversal risk is specifically marked as a key red risk.
Ah, that's a critical distinction, isn't it? The carbon is stored, but it's not necessarily permanently stored in the same way that putting it deep underground is. It could come back out.
Exactly. That's the core difference in the type of storage. The analysis also notes other risks, also marked red, like potential negative impacts on water systems if you plant the wrong species or plant them in unsuitable biomes. And limitations on overall capacity because of, well, competition for land. There's only so much land available.
Right. Land use conflict. What about cost?
Coast is rated orange in this analysis. So, not the cheapest, not the most expensive.
And the opportunities and threats side for ANR?
R&D activity is mixed, again, orange. Lots of academic publications reflecting ongoing ecological research, but low patent activity. Maybe because the basic technology planting trees is pretty well established.
Makes sense. Policy. Investors.
And again, similar story to DACCS here. Hampered by low global policy making, marked red, and a lack of investors, marked orange, needs more structured support to reach its potential scale.
Okay. So for you, the listener, thinking about ANR, planting trees definitely resonates as a positive action, right? And this analysis confirms it has high potential and strong public appeal, low energy too.
Right.
But the analysis also really underscores that while the carbon is removed, the storage isn't as fundamentally permanent as some other methods, like DACCS with geological storage. And those risks of it being quickly released again, like in a big wildfire, are significant challenges that differentiate it. It really comes down to the duration and the security of the storage.
That's a great summary of the trade-offs highlighted. Now, moving on, the thesis also looked at a couple other technologies it considered having relatively high scores in its overall assessment, just maybe with different profiles. Ocean alkalinization, OA, and soil carbon sequestration, SCS, fit into this category.
Ocean alkalinization. Okay, that sounds very futuristic.
Yeah.
Increasing the ocean's surface alkalinity somehow to get it to absorb more CO2 from the air.
That's the concept, yeah. And the potential scale is just immense, which the analysis definitely reflects. It scores green for long durable storage potential and marine sediment, potentially 100 to 10,000 years.
Okay, very long term again.
Low energy needs, marked green, and massive scalability potential, estimated up to 100 GTCO2 per year, a huge green. High potential contribution, green. And interestingly, high social acceptance, also green. Though the source notes this is based on low public awareness currently, but highly positive sentiment in tweets from the people who are actually discussing it.
Wow, okay, that scale potential is just staggering, 100 gigatons a year. But if it's not considered among the most promising overall in this analysis, there must be some significant downsides, right?
Oh, absolutely. Big ones. This is where the analysis highlights major hurdles. First off, it's rated red for very low TRL technology readiness level. The source indicates there's basically no mention of actual field trials in the literature they reviewed. It's very early stage, mostly theoretical or lab work.
Ah, okay. Very experimental still.
Very. And the risks are rated high, red. There's significant potential for local harm to marine ecosystems from changing the water chemistry, the pH balance, or maybe releasing toxic elements from the minerals used. Plus, potential impacts from the mining needed to get those alkaline materials in the first place.
Oof, yeah, ecological risks sound like a big concern there.
Huge. And measurability, the MRV rated red for low precision, is apparently very hard to accurately measure how much extra CO2 the ocean is actually taking up and storing due to this process over large areas.
Right, measuring things in the ocean is tricky.
Exactly. R&D is mixed. Orange, lots of publications exploring the concept, but no patents yet. Again, pointing to that early research phase. Cost is orange. And familiar pattern by now, low policy making, red, and lack of investors, orange.
Okay, So for ocean-based solutions like this, the potential scale is just mind-boggling, but this analysis really flags them as being very much in the theoretical or lab stage right now. Plus, they come with potentially significant ecological risks and major challenges in just verifying that the removal is actually happening reliably at scale. Lots of promise, but huge unknowns.
Precisely. A lot of work needed there. Now, the other one in this category, soil carbon sequestration, SCS. This is about using different farming and land management practices to enhance the amount of carbon stored in agricultural soils.
Okay, that sounds more grounded again, maybe closer to familiar practices for farmers.
It is, yeah. And the analysis reflects some real benefits there. High TRL, with some practices definitely into TRL 9. Lowest energy requirements of the methods looked at marked green. Often it just requires changes in how land is managed, not big energy inputs.
Low energy, that's good.
And it's rated green for cost, generally considered the most affordable approach per ton. Social acceptance is also high, green, again based on relatively low awareness, but positive tweet sentiment.
Affordable, low energy, high acceptance. That sounds very appealing. Where are the limitations according to this analysis?
Well, similar to A&R, the analysis points to durable storage being lower, marked orange, typically 10 to 1,000 years, and also subject to reversal risks if land management practices change back.
Right, it only stays stored as long as the practice continues.
Exactly. And there are other limitations, like soils eventually reaching a saturation point. You can only sequester so much carbon using a given practice. Maybe it plateaus after about 20 years or so.
Ah, okay, it's not infinitely cumulative.
Right. Risks are rated orange things like potential increases in N2O emissions, which is another potent greenhouse gas from changes in soil management. And soils are also vulnerable to climate change impacts, which could actually reduce their capacity to store carbon in the future.
Okay, and measurement, MRV.
That's orange too. Moderate precision for estimating the carbon capture, but limited precision for actually verifying the long-term storage in the soil across large areas.
And the big one's scale.
That's the main limiting factor highlighted here. Scalability potential is rated red. The maximum annual capacity is much, much lower than the others we've discussed. The source estimates around 9.3 million tons per year globally, which is just orders of magnitude less than the gigatons, the billions of tons, needed for the big climate goals.
Ah, okay. So SCS comes across as very accessible, low cost, low energy, leveraging practices people already know. That's a big plus.
Definitely.
But this analysis really underscores its limitations in terms of how long the carbon stays stored, the fact that soils can only hold so much, and critically, its much lower overall scale potential compared to methods like DACCS or ANR or even OA if that pans out. It might be great locally or as part of a mix, but the analysis suggests it's not a silver bullet for that gigaton scale global target on its own.
That's exactly the picture the analysis paints for SCS. The thesis also briefly reviewed some other technologies like BCCS, that's bioenergy with carbon capture and storage biochar, enhanced rock weathering, and ocean fertilization.
Right. And how did they fare overall in this SWOT comparison?
Generally, they received lower overall scores based on the factors used in this specific analysis.
Why was that? What were the main reasons they scored lower here?
Well, the analysis found they often presented a less favorable balance of the factors we've been discussing. Maybe higher risks associated with them, or lower technology readiness levels, maybe more limited scalability potential as assessed in this particular study, or lower measurability compared to the ones we focused on.
Any specific examples mentioned?
Yeah, the thesis specifically calls out enhanced rock weathering and ocean fertilization as appearing less promising for making a significant dent in the Paris Agreement goals, primarily due to high risks, high cost, especially for ocean fertilization, and particularly extremely low measurability, making it very hard to verify their effectiveness.
Okay, so the thesis's focus on DCCS and ANR as the most promising right now seems to be based on this detailed balancing act, weighing up technical readiness, potential scale, durability, against the risks and costs relative to all the other options reviewed.
Exactly. That's how the SWOT analysis played out here. And the analysis also pulled out some really important cross-cutting factors, issues that are significant challenges for almost all these technologies, pretty much regardless of their specific science.
Like the policymaking and investor incentives. We saw those were often rated low, red, or orange, even for the leading contenders.
Right. That came through strongly. The source highlights that dedicated global governance, specifically for CDR, is still very much in its early stages. It's happening mostly at national levels, maybe the EU level, but it isn't yet well integrated into the big international agreements like the Paris Agreement framework itself.
So there's no global plan or strong push yet.
Pretty much. And this lack of clear global policy direction, combined with insufficient investor incentives, is identified as a major overarching weakness. It's holding back the actual deployment of CDR technologies at the scale needed, even the ones like DACCS or A&R practices that are technically ready to go bigger.
So it doesn't matter how good the technology is on paper if there's no real policy push or financial backing to make it happen globally at scale.
That's a key conclusion coming out of this analysis, yeah. It also really stressed the importance of developing robust MRV methodologies that monitoring, reporting, and verification piece.
Why is that so crucial?
Well, the source points out that having reliable, trusted ways to actually measure the carbon that's been removed and prove that it's staying stored is absolutely fundamental. You need that to integrate CDR properly into climate mitigation strategies and official frameworks, especially when you think about things like international cooperation mechanisms, like under Article 6 of the Paris Agreement. If you can't reliably prove the carbon was removed and is staying removed, it's really hard to count it towards national targets or trade credits or anything like that. Right. You need accountability and trust in the numbers. Makes perfect sense. Okay, this has been a really fantastic deep dive into this thesis' analysis. Super insightful.
Yeah, it's a useful lens. And the main takeaway seems pretty clear, doesn't it? Hitting those crucial Paris Agreement goals likely requires not just drastic emission cuts, that's the priority, but also actively pulling significant amounts of CO2 back out of the atmosphere. Absolutely. And this analysis gives us a structured way to see that these different CDR technologies offer really distinct profiles. They have unique strengths, unique weaknesses when you measure them against these critical factors like potential scale, cost, risks, permanence, and how mature they actually are today.
And the specific conclusion from this particular thesis, based on its SWOT comparison, points towards direct air capture, with carbon storage, DACCS, and Afforestation, Reforestation, A&R, as having the most potential right now to make a significant contribution towards that sub 2 degrees C target.
Right. But the analysis is careful to highlight their very different challenge sets, isn't it? The high energy use and high cost for DACCS on one hand, and the questions around storage durability and those reversal risks for A&R on the other.
Exactly. And it also noted that ocean alkalinization and soil carbon sequestration show relative promise in specific areas, but they face different hurdles, like OA being very early stage, or SES having much lower overall scale potential.
But the source also really emphasizes that critical gap we talked about. Regardless of any single technology's individual promise on paper, that policy support and investor backing for CDR at the global level are still really underdeveloped. And that's a major bottleneck for scaling anything up to the levels that the climate science says we might need.
Absolutely. It's a recurring theme across the board.
Which actually leads to a really interesting thought to maybe leave you, the listener, with. It draws from the source's look at social acceptance using that Twitter data. The thesis found that while general public awareness of many specific CDR technologies seems pretty low, the sentiment among the people who are discussing them online is often quite positive, especially for things that sound familiar, like planting trees with A&R, or seem accessible, like soil carbon sequestration.
Interesting observation, yeah.
So, considering the absolutely massive scale that the IPCC suggests might be needed for CDR to play its required role alongside emission cuts, how much does public understanding and maybe widespread public support actually matter in accelerating the development and deployment of these crucial, but maybe sometimes controversial or expensive carbon removal solutions fast enough?
That's a great question. How much does that social license really influence the speed and scale?
Yep.
Definitely something worth pondering as these technologies continue to develop and potentially become a much bigger part of the climate conversation.